Today we're going to be talking about compound linear inequalities in one variable. And what do we mean by this? Well, each part is still going to be just like the simple linear inequalities we looked at last lesson, but by the compound part, that means that we are somehow combining two different inequalities into the same thing. And there's two different ways that this can look. They can be an and statement. Well, we're talking about two inequalities being true at the same time. And what do we mean by this? Well, if I say that x is less than 4 and x is greater than 2, or let's say greater than or equal to 2, what I'm saying on the number line is that for both of these to be true at the same time. So I would need that x can be bigger than or equal to 2. And that x can be strictly smaller than 4. So then what I want to find is this overlap region, that if both of those statements are going to be true at the same time, this means that x must be in between 2 and 4, but inclusive of the 2. So I would, in interval notation, write that he would be in between 2 and 4 with a bracket on the 2 because he would be included, a parenthesis on the 4 because he would be not included. These can be written two different ways. Sometimes we do this double-sided inequality where by convention both of these inequality symbols are going to be less than symbols, and you're always going to list the smaller number first and then the larger number, so that the x looks like he's physically in between those two numbers. Other times we may physically break it up into two different inequalities. So we might give one bound, connect with the word and then give the other bound. And that would be fine too. And in this case, that would be that bound, and then this one will be the other bound. So you're connecting the two of those at the same time. Both of those are the same thing. Tomato, tomato, you're allowed to use either notation. You'll probably more often see the one where he's trapped physically in between them, that three-sided inequality, but both are totally fine. So let's take a look at another example. So if I say x is less than 7 and x is greater than or equal to 3, well, if I were to visualize that on a number line, that means x has to be strictly bigger than 3, and it has to be or not strictly bigger than or equal to 3, and it has to be smaller than 7. So x is going to be trapped here right in between 3 and 7, inclusive of the 3. So if I were to translate this to interval notation, I would say the smallest number it can be is 3. I'm going to do a bracket because it includes the 3. And the biggest number it's approaching is 7, but I'm going to do a parenthesis because it doesn't include the 7. The way that you would rewrite this as a three-sided inequality is you would keep the x is less than 7 the same, but when you flip around the 3 to be on the other side of x, that greater than or equal to sign becomes a less than or equal to sign, and then you have the 3. And then if you were to read this statement from left to right, it says 3 is smaller than or equal to x, logically equivalent to x is greater than or equal to 3, and x is smaller than 7. The other type of compound inequality there is an or statement. By convention, we do not use triple-sided inequalities for or statements. If you see a triple-sided inequality, it implies and I'm actually going to write that. So triple-sided inequality, or triple parts where there's 3 parts to the inequality, that's always going to imply and. For or, we're always going to use the word or every single time. You need to find the word or for it to be an or statement. If you're going to be using interval notation, the way we talk about or is this right side up U symbol. It's not literally a U, but it looks like a U. That's called set notation. If you ever go deeper into math, like beyond calculus, you'll see that set notation a lot. Otherwise, this is kind of the main place you see it is when we're talking about inequalities, because we're talking about sets of solutions. So whenever you see that little U, that means or. Technically, there is one that means and, that's upside down. That's not as commonly used because, as we saw earlier, you're probably just going to put things together into the same interval. But the upside down one does technically mean and if you see it. what you're actually going to use a lot is this right side up one, meaning or. That's actually very commonly used. And if it's a non-trivial or statement, you're going to have two different inequalities going in two different directions. And by non-trivial, I mean it's not an or statement that's giving extra information. Because if I said that x is bigger than 1 or x is bigger than 2, that's kind of silly. Because if only one of those two statements has to be true at the same time, all numbers that are bigger than 2 are also bigger than 1. So you would just say x is bigger than 1 is like the simpler way of saying it. That would be kind of a little bit of a trickier situation where it's helpful to graph it. But if it's going to be non-trivial, that means you're talking about two different sides of the inequality being shaded in opposite directions. And what do we mean by that? So if I say x is less than -3 or x is bigger than 7, that means, because there's only the word or, that means one statement only has to be true, logically speaking. Don't need both statements to be true at the same time, just one or the other, hence the word or. When it's and, both have to be true, which is why it ends up being this overlapping region. When it's or, just one has to be true. So we have x is smaller than 3. I'm going to use an open circle, or smaller than -3. Going to use an open circle because I'm not including the -3 and shade to the left because it's smaller numbers. Versus x is bigger than 7. I'm going to use an open circle because it says strictly bigger than. I'm going to shade to the right because it's greater than. And then to translate this into interval notation, this first part would be that the smallest bound is it's going towards -infinity because it's going forever to the left, comma, -3 is the upper bound, but it's a parenthesis because it does not include the -3. Union, so this little right side up u, that means or, so or. 7 is the lower bound of this section. Infinity is the upper bound of this section because it's going forever towards the right. And then both of these get parentheses because the 7 is not included, and both infinity and -infinity always use parentheses because we never can actually reach them. And that would be how you write that in interval notation. And again, this is kind of two quintessential examples of non-trivial statements. Occasionally in some courses you may come across situations where they're trying to get you to write it more succinctly, like we were noting over here where they really gave you extra information. You should have just written it as a single inequality. Those are not as common of situations, but they're worth keeping in mind, which is why you should always really graph the solution that you're talking about. So now we can revisit this chart and we can really focus on the fact that these top 4 are all different situations of and statements where you can talk about the two bounds that you're trapped in between. So you always want to use a bracket when it includes versus some sort of parenthesis when it's not included. That's really the key part. And you know if it's included if it has the line underneath versus there will be no line underneath if it is not included. In order to solve compound inequalities, you really want to solve them independently and then just put them together at the end, just kind of treat them like two different linear inequalities. And if it's a three-sided inequality, you kind of have two choices. You can go ahead and just split it up into two separate inequalities that have the word and in between, or you can also just solve all three sides at once. Then you want to graph the solution at the end to see if there's a simpler way of expressing that inequality. And what do we mean by that? So let's just actually do sort of a simpler example here. So let's say we have, and we'll make that a -1 here. -1 is smaller than x minus 3, and x minus 3 is also smaller than 2. How would I solve it? Well, there's two different methods. I could just treat this as three-sided. So I'm going to rewrite this where I can just treat it as three-sided, where if I'm going to undo subtracting 3 in the middle, I also need to undo subtracting 3 on both sides. -3 plus 3 makes 0. That cancels. -1 plus 3 gets us 2. And then 2 plus 3 gets us 5. So I have just confirmed that x is physically in between 2 and 5. That's one way to approach it, and then you would say 2, 5 both with parentheses because the 2 and 5 are not included, would be your solution. Alternatively, you can physically break it up into two inequalities with the word and in between it. What do we mean by that? We mean -1 is less than x minus 3 and x minus 3 is less than 2. You would get x by itself in both cases by undoing subtracting 3 by adding 3. You would get 2 is less than x and x is less than 5. You may want to rearrange this so that x is written first, so you'd get that x is greater than 2 and x is less than 5. And then if you were to graph it, you would be looking for their overlap. So for x is greater than 2, you're going to use an open circle on 2 and shade to the right because x is larger. For x is less than 5, you're going to use an open circle on the 5 and shade to the left because x is smaller. And that means its overlap region is exactly the same as what you found before, just right there in between. So your solution would be 2 being the lower bound, 5 being the upper bound, both not included. Just something to kind of keep in mind. And we'll do some more examples of that in a second. But keep in mind that oftentimes real-world problems might phrase those and inequalities by just saying that you want to spend in between, that you want to be between these two values. So every time you see between, you should be thinking this is some sort of and statement, just as kind of a quick note. And if they say inclusive, that means you need that or equal to sign, aka you need to include those brackets. Otherwise, kind of interpreting inequalities, or compound inequalities in a real-world scenario is very, very similar to those simple linear inequalities we went over last time. So let's kind of dive into what is a little bit different, which is this solving a little bit more. So we looked at kind of a simple one-step example. Let's look at a two-step example this time. So again, for these, I'm going to still kind of show two alternative methods. You can do this either way. So if you're comfortable, you can take this triple-sided inequality and just do operations to all three sides of the inequality. So you would say, okay, well, normally if it was 4x plus 9 is less than 13, the first thing I would want to undo is adding 9. That's exactly what you're going to undo first here too. So 9 minus 9 is going to make 0 and make that 9 go away using that inverse operation there. Negative 15 minus 9 gets us negative 24 is less than or equal to 4x, which is less than or equal to 4. And then as a final step, you're going to undo multiplying by 4 by dividing by 4 on all three sides. So then you get x is smaller than 1 and greater than or equal to negative 6. That's one way to approach it. Or you could physically break it up into two inequalities. So you could have negative 15 is less than or equal to 4x plus 9 and 4x plus 9 is less than 13. So when you break it up that way, they basically share this middle portion, and that's what gets repeated. Then your actual steps are going to be identical to what you did before. You're still going to undo adding 9 by subtracting 9. Do that to both inequalities. And then undo multiplying by 4 by dividing by 4, making 1x. Still has the word and in between, and then I would recommend rewriting this first one so that x is first. When you rewrite it where x is first, you got to flip around the inequality symbol because negative 6 is less than x is logically equivalent to x is greater than negative 6. And then either way, when you graph this guy, negative 6 is your lower bound, 1 is your upper bound. On this second one, I made the mistake of dropping the or equal to symbol there at the end. You don't want to do that. You want to always kind of double check that your symbols sort of match the original symbols that you had. So that means because the 6 has the or equal to symbol, he is included. So I'm going to shade him in with a closed circle. Because the 1 does not have an or equal to circle symbol, he's going to be an open circle because he is not included. And then either way, what I've really expressed is that x is in between them. Either by thinking about it, the x is physically trapped in between them, or if x is larger than negative 6, that part would be shaded to the right, and smaller than 1, that part would be shaded to the left, and that means their overlap region is right there in between. So if I wanted to express this in interval notation, that would be negative 6, comma 1, with a bracket on the negative 6 and a parenthesis on the 1. Now, while I showed you those two different methods, that gets kind of difficult for this next type of problem. So if you're going to do the triple-sided inequality by doing operations to all three sides, I really don't recommend that in the situations where you've also got x's on the left and to the right. Because if you tried to do that, let me show you where that would go wrong. If you just subtracted 8, subtracted 8, subtracted 8 to get x by itself, then I have 2x minus 1 is less than x, which is less than 3x plus 4, which is true. And I've gotten the x by itself in the middle, and I have no idea how to graph this guy because I've still got too much going on the other two ends. So in a situation like this, I would just stick with the second method I showed you there. You might have been wondering, why did I even show you the second method? For situations like this, where really it's just not practical to just do operations to all three sides. You technically can, but it gets a little messy and you're apt to mess up something somewhere. I'm a mathematician, I don't trust myself to do it that way. Just actually break it up into two inequalities. So what do we mean by break it up into two inequalities? Well, these two inequalities are going to share the middle part, and then otherwise you're going to have one that's this first statement, and you're going to have one that is the second statement, and because it's triple-sided, it's implied to be connected with the word and. So let's go ahead and write these guys. So you've got 2x plus 7, and actually let me just differentiate this from the previous problem, is less than x plus 8, and then you have x plus 8 is less than 3x plus 12. And just like with linear inequalities, once you're here, just treat them as two separate linear inequalities, and I would recommend keeping your x's on the left, just so that you kind of best know how to connect these guys, because we do read left to right generally. So if I'm going to be moving all my x's to the left for this first one, that means I'm going to subtract x, then I would have x plus 7 is less than 8. And then if I want to keep on going, again, my goal is to get x by itself, so I'm going to subtract 7 from both sides. So I get x is less than 1. Same deal with this next guy. I'm going to first move all my x's to the left, so I'm going to subtract 3x. Negative 2x plus 8 is less than 12. Again, my goal is to get x by itself, so I'm going to want to move all constants to the other side, so I will subtract 8. Negative 2x is less than 4. Then as a last step, I'm going to divide by negative 2, because my goal is to get a single x by itself. Negative 2 divided by negative 2 is 1, and I want to be careful that whenever I divide by a negative on both sides, I need to flip around that inequality symbol to make that x is greater than negative 2. Notice how I did not have to divide for the previous problem because I was dividing by a positive 4. Even whenever I had, in this example, a negative 24 divided by positive 4, that's fine because the number I was dividing by was still positive. So we were okay. We did not have to flip around that inequality symbol. Then to actually graph this, we want that x is strictly less than 1, so I'm going to use an open circle on the 1 because he's not included, and then shade to the left because he's smaller than. And we want x is strictly bigger than negative 2, so I'm going to use an open circle on the negative 2 because he is not included. Shade to the right because he's bigger than, and then lo and behold, their overlap region really is the place just in between. So then our final solution would be that x is in between negative 2 and 1 with parentheses on both because those values are not included. And then you could write the inequality two different ways. You can either write x is less than 1 and x is greater than negative 2. That's a totally fine way to write it. Or if you're going to do it the triple-sided inequality way, you're going to keep the inequality that still has a less than symbol as is, but you're going to flip around the lower bound so that you're talking about how that lower bound is smaller than x to make that nice triple-sided inequality. The way that you'll know you did the triple-sided inequality right is the order of the numbers should be the same as the order that you would use in that interval notation. Sometimes they already give you the problem where it's split up with the word and then you want to keep in mind that and means you're looking for the overlap because both statements have to be true. Statements, both inequalities, need to be true at the same time. And by that we mean whatever number we get as a part of the solution set needs to be plugged into both inequalities. I would encourage you to go ahead and pause your video and try these next two yourself, and then we'll go over those solutions together. So for the first part, you're really just going to treat these as two separate linear inequalities, but you're going to combine knowledge about the solutions at the end. So for this first one, this looks like a nice two-step guy where I've already got all my x's to the left, and then I want to go ahead and move all my constants to the right. So I'm going to subtract 1, subtract 1. I'm going to have 2x is less than or equal to 4. Then I want to still get a single x by itself, so I'm going to divide by 2 to undo multiplying by 2. And then I get x is less than or equal to 2. Then I'm going to go ahead and solve my other inequality. Same deal, I'm going to undo subtracting 4 by adding 4 on both sides. 3x is greater than negative 1 plus 4 gets us 3. And then as our next step, we're going to undo multiplying by 3 by dividing by 3 on both sides, so then I get x is larger than 1. Then in order to visualize on the number line what my solution set is going to be, for the x is larger than 1, I'm going to use an open circle on 1 because he is not included, and shade to the right because it's greater than. And then for the 2, I'm going to use a closed circle on the 2 because he is included, and shade to the left because he's less than. So my total solution set is going to be that x is in between 1 and 2, not inclusive of the 1, so he's going to use a parenthesis, inclusive of the 2, so he's going to use a bracket. Or if you were to make it a triple-sided inequality, you would have x is smaller than or equal to 2, and it's strictly bigger than 1, because that is the logical way to sort of flip around this inequality, that if x is greater than 1, that means 1 is smaller than x. Or you can just write it with the word and in between. So you can say x is less than or equal to 2, and x is greater than 1. That's a completely fine way to use it as well. For this next one, same sort of process, but keep in mind this time it's broken up with the word or. So if you see the word or, that means only one, and actually let me flip around where that arrow's going. Only one of the inequalities needs to be true at once. That's why it has the word or in between. Chances are for a number in the solution set, it's only going to be true for one or the other inequality. It's not going to be probably true for both at the same time. If it was true for both at the same time, there was no reason to express this as a compound inequality. There's probably a simpler way to express the inequality. So let's go ahead and solve these guys. So for 4x minus 1 is greater than 11, you will solve that by first undoing subtracting 1 by adding 1 on both sides. So you get 4x is greater than 12. Then we're going to undo multiplying by 4 by dividing by 4 on both sides. So then we end up with x is greater than 3. For the second one, again, we're just really solving these as though they're just two totally separate linear inequalities, and we'll kind of put the knowledge together at the end. For 2x plus 3 is less than negative 5, we're first going to undo adding 3 by subtracting 3 on both sides. End up with 2x is less than negative 8. Then we're going to undo multiplying by 2 by dividing by 2 on both sides. So we get x is less than negative 4. Notice how I did not have to flip around the inequality because I'm dividing by a positive, so I'm good to go. Then if you wanted to plot this, again, only one or the other has to be true at the same time. If I have a negative 4, I'm going to use an open circle on him because there's no or equal to sign, and then I'm going to shade to the left because it's strictly smaller than. For the x is bigger than 3, I'm going to use an open circle on the 3 and then shade to the right because the x is strictly bigger than. Then to actually write the solution set, I'm going to say the first inequality that goes from negative infinity, because it keeps going forever to the left, up to negative 4. And then I'm going to use a parenthesis on the negative 4 because the negative 4 is not included. Union, so or, that's what this U means, is or. 3, comma, infinity. 3 has a parenthesis because he is not included. Infinity and negative infinity philosophically always have a parenthesis as well because we can't ever reach them. And that arrow going forever to the right means we're going up to infinity. And then if you want it in words, it would just be exactly written as is. So depending on what notation you want, either inequality or interval notation. Go ahead and pause your video and try this next one yourself, and then we'll go over those solutions together. So for this next one, again, we're just going to treat them as two separate inequalities and then connect them at the end. The plus 0 being written is a little bit silly, but that's probably because the computer program sort of randomly generates these numbers. But we want to move all of our x's to the left and keep all numbers to the right. So we're going to undo negative 4x by adding 4x on both sides. Negative 4x plus 4x makes 0. That's how we're able to quote-unquote cancel it out. Negative 3x plus 4x is actually just a single x. I'm not going to write the plus 0 because it's an additive identity. It doesn't really do anything. Is greater than 7. And actually, that part's already solved. That's pretty nice. For the next part, we're probably going to want to simplify this left-hand side before we start moving stuff across the equal sign. So first we're going to distribute the 2. 2 times 4x is 8x. 2 times negative 3 is negative 12. Drop down the plus 8, greater than or equal to, drop down the 10x minus 4. Then we want to combine like terms within one side of the inequality symbol. So in particular, negative 12 plus 8 is going to get us minus 4. It's greater than or equal to 10x minus 4. Then we're going to keep on going, and we do want to be in the habit of keeping x's to the left and numbers to the right because it can make it easier to read off. So then we're going to subtract 10x, positive 10x minus 10x makes 0, 8x minus 10x makes negative 2x, drop down the minus 4, drop down the other minus 4, undo subtracting 4 by adding 4 on both sides. Actually kind of both cancels, which means we just have 0 left here on the right hand side. But then we still need to get x by itself. Currently it's being multiplied by negative 2, so I'm going to divide both sides by negative 2. And that's good to keep track of because when I divide by negative 2, that's going to flip around that inequality symbol, so that's now a less than symbol. Then if we're going to go ahead and graph these, for x is less than or equal to 0, less than or equal to, so or equal to, we're going to shade in the 0, and then less than, we're going to shade to the left. For x is greater than 7, we're going to use an open circle on the 7, and then we're going to shade to the right because it's strictly bigger than 7. So as our final solution, we can kind of put this in interval notation. Going forever to the left means that it is a negative infinity there, comma 0 is the upper bound of that section. We're going to use a bracket because the 0 is included, hence the or equal to sign and the shade and circle. Union for or. And then 7, we're going to use a parenthesis this time because he's not included, comma, positive infinity because it's going forever to the right. And then both infinity and negative infinity philosophically always get a parenthesis. Or you can just write it in words, x is less than or equal to 0, or x is greater than 7. And then I just want to make a very quick note about some sort of like special case scenarios you may occasionally run into. If you had that x is bigger than 0 and x is less than 1, let's say. Actually, wait, I'm actually going to write that as and x is less than negative 7, let's say. Well, if you tried to plot this, 0 with a here, negative 7 over here, if this is an and statement, these never overlap. So that would actually be considered no solutions. So keep that in mind. That doesn't happen very often, but if you get an and statement where they never overlap, that is a no solution situation. There has to be some overlap. Nice and statements will consistently work out where you've got this nice in-between region being shaded in, but it's always worth actually graphing because if it ends up graphing like an or statement, but they claimed it was an and statement, that means there's no solution there, and it was actually, I hate to say trick problem, but it's a problem that wasn't solvable. No solution in that case. So always be in the habit of actually graphing it out, just in case you do run into one of those kind of special case scenarios.